summer school here. If I was postdoc for 1 year, but there was also a summer school on birational geometry. So 18 years after, we come back to birational geometry. So I'm sorry for some people will probably sleep during my talk because I will be very elementary. I was planned to be at the beginning, but I couldn't come yesterday, so that's why I start today. But it will be probably the most easy talk, I guess. So we'll speak about Cremona groups. Cremona, that's the title of the lecture series. Group of rank 2 and rational surfaces. Okay, so we can say a lot of things on the Cremona group, and many of them are not completely easy, even in dimension 2, but I will start with really something very simple today, and I will go a bit more difficult things afterwards. So I think Michel, because I saw the notes of Michel that he defined what is the Cremona group yesterday. So you know what it is. So I will speak about this group, P2, which is a set of birational maps from P2 to P2. And usually what I will do, I will see this with geometry, so with sequence of blow-ups and contractions. But I will also write it sometimes with explicit maps. So you can sometimes write it with coordinate map like this. Or you can write it with a coordinate map like this. So this is the standard involution. And I will try to prove probably tomorrow, or maybe, I don't know how much time it will take, but during this week at least, that you have the theorem, Noether-Castelnuovo. Then that this group is generated by automorphism of P2. This is PGL3 and sigma. So I didn't define what is my field. So in this talk, K will be algebraically closed. So otherwise it's false. Okay, so I will prove this. So it's not so difficult, in fact. There are many, many proofs. I gave them. For example, a master student of me studied this in the beginning of master thesis. It's maybe 2 weeks to learn this with basic algebraic geometry. Okay, so I will try to prove that probably tomorrow. And then beginning to see this, we will see this with geometry. So with blowups, we'll see that sigma is blowups 3 points and contracts 3 lines, and then use the sigma and use the Jonquière maps to prove this. Will be essentially the proof of Castelnuovo. Okay. Yes. Yes. You want, but my course is on this. So. Remark, maybe, if we didn't assume then the result is false. But this is a remark. This is a theorem. This is really, really easy. This is really an exercise for any K. And basically, you just write a hint for the exercise. Look at xy on A2 xy goes to x, y times a polynomial of x. So if it's not algebraically closed, you can take it irreducible, but not of degree 1, and this one will be not there, not in this group. Okay, but it will come after. My course is on algebraically closed, so I cannot prove this. But maybe at the end I will remove this at the end of the. But if you know what is not algebraically closed, you can prove this. Okay, so I will try to explain this. For this, I will need to look at some surfaces, so blow-ups of P2. I will show you also, en passant, some del Pezzo surfaces that I don't really need for this result, but that are interesting for studying finite subgroups. For example, of Cremona group is very interesting to have the del Pezzo and some conic bundles. And I will have also to define irreducible surfaces. This will be very useful for this. Okay. Okay, then I will start by blowing up some points. So as I saw this morning, you already saw many times blow up in these talks. I will define what it is, but probably you have seen it before. So, okay, what is the definition? This was already chapter 1. This is chapter 2. It's very quick. I have some notes I will put online, but I'm always very sketchy, so I do it at the end. So I didn't send it to Michel because I didn't finish it. So we have the blow-up of A2. I will define it like this. I mean, you have your own definition. If you have your definition, you will see that it's the same as my definition. I will define this as the set of points x, y, u, v in A2 times P1 such that xv equal to yu. Okay, so this is my definition for the blow-up, and then I have a morphism pi to A2, which is just the first projection. Okay, so in the literature you have the blow-up is many things. It can be this surface, it can be the morphism, it can be even the map in the other directions. So all of the three are correct. So, so it depends on the context. Okay, so for me the blow-up would be for this course I would be saying that it's this variety with the morphism. Okay. Okay, so this is the blow-up of a point. So pi, the morphism is the blow-up of 0 in A2. 0, it's 0, 0. The origin, and this is the, I would say, kind of definition. In general, if you want to define the blow-up, you can do it more intrinsic. You can take a point in a variety, and then you look at the some functions locally. You can just, what is very important, you can do everything locally. So you have your variety, you have your point, you take an open subset there, and then you will define it only on this open subset. And on this place, you can take rational functions, which are defined at the point, which generate the ideal, and you just take a graph like here. This is the blow-up. You have the map from here, from the inverse map, from here to here, it's the map. xy goes to xy, xy. So this is the inverse, it's birational. And then you just take the graph of a map like this, and this is the blow-up of a point. So you need to take enough coordinates in general to have to generate the local ring of functions defined at the point, and then it will be independent of the definition. So this is for a local definition, and then outside you do nothing. Okay, so that would be the definition, but for A2, then it really is very nice. And now you can look at this geometrically and see that if you have, in our case, we have the point, and we have colors. Yes, colors. What is important, if you want to play with this, you have the point, which is in A2. So this is the picture in A2. And then you blow up this point. What is the pre-image? So this is P, which is 0, 0. And this is pi minus 1 of P. If you look at the pre-image, you see that if x and y are 0, this equation is satisfied. So it's just 0 times P1. So it's a P1. And okay, maybe this color is not so, you don't see the difference. Okay, so you have one P1 for one point, and outside of this you have a bijective map, because if you take a point here where this is not 0, this equation tells you exactly that this vector is a multiple of this one, as a in algebra, just determinant is equal to 0. So it just says that the point of P1 is uniquely determined. It's just this point. So this is bijective. So outside you do nothing. But what is interesting is looking, for example, at the lines here. This is, for example, y equal to alpha x. Then if you take a line like this, you can parameterize it. You can, as t goes to t alpha t. And when I look at this map, outside of the point, at the point I have no image. I don't know what is the pre-image. So then I have t alpha t, but because if t is not 0, then I can simplify. And then afterwards I have a curve, and here, if you have this correspond, like I will say L alpha tilde, then this point will be 1 alpha. So the important thing is that here you have many lines which intersect, and upstairs they are disjoint. Okay, so you separate the directions. So what you should keep in mind for the blow-up, you replace a point by a P1, and the P1 is exactly the projectivization of the tangent space. So it corresponds exactly to the directions. And if we have a, a conic, then it will pass, it will be like this. It will pass through one line. Yeah, there will exactly one line here, passing through the point which cuts, and which one exactly the one where it is tangent. Okay, so that's the main thing for the blow-up, and then we will, what is this group is composition of Barashna maps, which are just of this type, locally just that. Okay, so it seems rather simple, but if you do this first in this direction, the other direction, you do a lot, it can make a complicated group. Have questions? Of course you don't have. Okay. Now, in general, you can do a blow-up in P2 or in Pn. I will, that was definition 2, 3. So I take in Pn, I have the same kind of constructions. You have a this is x0, xn, y1, yn, and then I take this and I ask xi, yj equal to xj, yi for all ij. I take this one. Okay, I didn't say something, but before, what is important is that this surface is smooth. You have two charts. Maybe I will just tell you. You have two charts. You have the points where u is equal to not 0. U is not 0, which is, if u is not 0, then you can assume to be 1, and then you have y equal to xy. And then you have y equal to xv, sorry. xv, and then 1v. And then you see now that it's the same as A2. Okay, so you have one chart isomorphic to A2, and the second one, you choose v equal to 1, so x is yu. So you have two charts. And then it's a union of two charts which are A2, so it's smooth. And also it means that the map, the blow up, sometimes the people see is locally as xv goes to xv. Because you have an A2 there, and the map is just this. And if you look at the other one, it's just coordinates. You change the coordinates, so you have the same behavior. And when you do this, it's not the blow up. It's a local version of the blow up. You have lost one line, one of these lines, which is when v equal to 0. Okay, so you replace your A2 by some variety which is a copy of 2A2. In some sense, the next one is a bit bigger. It has one curve more. Okay, and it makes sense, in fact, to say this. We can really say that it's bigger. Okay, now I'll do this for projective. In general, so you could take n equal to 2 and now you have P2 blown up, but this is in general. And now you have the map with pi to Pn, which is again first projection. And this is the blow up pi. Of 1, 0. Again, the inverse is birational. The inverse, it sends so if you have these equations means exactly as I said before, that the vector space the vector x1 to xn and the vector y1 to yn are collinear. This exactly means this. So if it's not 0, then it's unique, and it's this one. Sorry. That's the first coordinate. And then you have the graph. This is the graph of the map that I just wrote before. And then you have this. Okay, so this is when it's not 0, and when it's 0, but it's not defined. And the preimage of 0 is a whole Pn minus 1. Okay, so now it's a blow-up of point in Pn, and in general, what you can do is you can take any variety. Yes, I will take any variety. Or maybe first I just will define what is a strict transform. So if you have x in Pn, locally closed, then what you can define is x tilde, which is in y. You want to take, in some sense, the preimage, but if you do this, the same as before, if you take the preimage of a line to the point, you get the line that I brought on the top, plus the preimage of the point. So you get too much with the preimage of the point. So I would like to say that when I take this, the tilde is the strict transform. So the same as here. So how do you define it? You take x minus p. And then if you do this, you have forgot one point. So in my case of before line, so I have to take the closure. And if x is not closed, then I just want to be sure that I don't get too much. Okay, so this is the strict transform. Strict transform of x. So outside of the point where it's an isomorphism, I just take the preimage, and then I add some point in the preimage of P, and it's given by closures of points which are outside. Okay, so this is my strict transform, and so an example. If I take some lines like before, same as before, then if I have L in Pn, line through T, then it's the image. You have a map U, V. So it passed through 1, 0, 0, and then it will be like this. U, A, 1, V. Okay, and then the A1, in fact, it's A1 into En is in Pn minus 1. If I change by multiple the AI, it's change the parameterization, but not the line. So it's just the point of Pn minus 1. It's all the lines through the points which are parameterized by this. And now I take L. This is just the image. Is the image of now you take the map, the same map, but you look it on the blow up. And then it will be AN. Okay, you see that if it's V is not 0, then I have no choice for the map. It will be A1 to En times V. It's the preimage, but then I can divide by N and it's constant. So if I take the closure, it will stay constant. So the preimage of the... So all the lines, the strict transform of the lines are exactly the preimage of a point in Pn minus 1. You have a P1 bundle when you project on the second coordinate. And this corresponds to the same picture as before, but in any dimension. So we have looks like the same, but it's in the higher dimension. Maybe I will do it like this, that you see the difference. When you blow up a point, you get this. Okay, so that's for a point in Pn. And why do you want to do it in Pn if you want to study surfaces? Because in general, if you take any algebraic variety, for example, I will blow up P2. So P2, the blow up of P2 is just this guy with n equal to 2. But the blow up of P2 blown up at a point, what it is. Then if you want to define it, you could do say with the intrinsic definition I get, but you can also say it like this. You take Z algebraic variety. So let's say quasi-projective. Then you have, you can embed this in Pn, locally closed, subset. You have a point there. You can choose that the point is sent to 1, 0, 0. And then you look at my map of before, and then you have the Z tile here. This is the blow up of P. Okay, if you do this like this, it's not clear that it's just dependent of P, but in fact it is. If you have two different, if you have Z in Pn, you put it in P n plus 1, or anything n prime, and then you have the blow up, and then you have inside Z tiled for two different Z tile, I would say prime, then you have an isomorphism, unique. So it's really uniquely defined, so you have only a probability point. So now we can define blow-ups for a point in P2, and then a point in the blow-up of P2, and blow-up of P2, and blow-up of P2, etc. And then it has no end, because each time you blow up, you have a P1, you replace your point by P1, so you can continue to blow up something here. Okay? Oh yeah, it's very slow. When I was young, I was here, and they told me the first week is for master student, the second is for PhD, the third is for a researcher, and they said this, but it was false. So I was postdoc, it was hard already the first week. So I tried to have my revenge and to do things slower. Okay. I had troubles the first week, but I could follow. Okay, then we will blow up some points in any surface. And what is interesting with this is that if you blow up some projectivity, it stays projective. If you blow up something affine, it doesn't stay affine. Neither projective, neither affine. What you get is just quasi-projective. So you blow up something quasi-projective, it stays quasi-projective. You blow up something projective, it stays projective. And you blow up something smooth, it stays smooth. Okay, because me, I just blow up points this week. Okay. Good. Now, why is it interesting? I already said it, but I will write it as a proposition. I will not prove it. You can see it in a Archon if you want, for example. It's not his result, but if you want a reference. Okay. Then you have a eta, x to y, birational morphism. So it's birational map which is defined everywhere. And then between smooth projective. Projective surfaces. Then it's essentially a sequence of blobs. Then there is a x2, x1. There exists. So x will be xn, n plus 1. Xn minus 1, sorry. 1. 0, which is y. It's maybe strange. Call them x, maybe. Then this would be pi. Well, it's not very important. Pi n. Pi 1, the first one, okay. And watch pi I from xi to xi1 minus 1 is the blow up of a point pi, which is in xi minus Okay, and what is important is that this map's composition is the eta. This direction. So usually you write it from the, you first do Pn and then Pn minus 1, because in fact you start usually from here. Here I start from here. Okay, so how you can prove this? I will not prove it, but not sure. Well, maybe I will prove it. If you take a point here where you take the preimage, the map in the other direction, you have some points which are not defined. When it's defined, it's an isomorphism. And if you have points which are not defined, you blow it up, and then you have to use a universal property and show that something decreases. It's not completely easy, but you can do this. Okay, so important fact-wise, important the blow up is that any birational morphism is like this, and then afterwards we'll do every birational map, and we will see this as a composition of two. You have a diagram before. So for the ball is morphism, but afterwards any birational maps. So even if it's not defined. So here for me, birational morphism is birational map defined everywhere. I know that in Russia it's not like this, because I worked with many Russians and they say birational morphism it's the same as birational map. Okay, so me, I assume that it's really defined everywhere. What is important now is that if you have the pi, I would say this is a blow-up of n points. Usually we say this. It's a blow-up of n points. But the points, they are not really in y. The first one is in y, but the next one is in x1, and the next two, and so on. So in fact, the pi, here you have p1, 2, and so on. So in fact, it's just only one point in y. But in fact, the main thing, I think it's already used this morning by Christian, is that if you have 2 points in a surface, and you want to blow up the 2 points, I didn't define what is the blow up of 2 points, but we could also define it. In fact, what I do, I would like to blow up first P, and then I get a surface there. And now I have replaced the point by a curve. And outside of this, it's an isomorphism. So in fact, this point, it corresponds to a unique point there. So in some sense, I would like to call it Q. Not really Q, it's another point. I will see it after. And then the same here. If I blow up this point Q, and then I have also the point here, which should be P. In fact, it's not really P, but I would like to call it P. And then afterwards, I can blow up P again, here and Q there. In fact, it's the same. What you can show is that the same variety on the top. You have a commutative diagram. And the reason is just because the blow up is locally given, so you have an isomorphism outside. You can just look at what happens here. So from here to here, you have an isomorphism, but it's exactly the same as what happens here. The diagram commutative. Okay, so here, when I say the points, I would like to say then that the point here is in y, but the next one could be also in y. I mean, if it's, I blow up my first point, and if it's a point like this, in some sense, I want to say it's a point in y. But sometimes it's not possible, because if I blow up now a point which is exactly here on this curve, it will not be possible. Here, it's not really a point of y in any sense. So that's what we come to the what people call bubble space. Okay, so maybe it's at the beginning of things. They are a bit more technical, but should be okay, I hope. Otherwise, ask me. So now we take X, smooth projective surface, and we will define bubble space. of x. Okay, so what it is, if you want to make it formally, definition, it's triplets where you take y, and pi. So you have pi y to x, irrational morphism. Y is a smooth projective surface, and y is in. Okay, so you take just triplet like this up to some equivalence. So I will say what it is, the equivalence. But you take, by this result, you take just, maybe it's not good, I exchange x and y, so I'm completely independent of the letters. So. For me, these are all free variables. Okay, so I take something down, and then I go up by some birational map, and I take a point there. Okay, so, but this, as I explained, this is just a sequence of blow up. So you blow up some points on a surface, and then you pick a point on the top. Okay, and the important thing is the equivalence. So y pi is equivalent to another one. So you take y prime if you have, I will make a picture, you have y, you have pi prime, y prime. So both are birational. So you can compose these maps. Birational, it's an isomorphism on the open set, so you can compose birational maps, it stays birational maps. So now you have pi minus 1 composed with pi. So you have birational maps, maybe it's not defined everywhere, but you ask that this is is a local isomorphism at y and sends y onto y prime. So what does it mean? It means you have a local isomorphism. It means you have an isomorphism between two open subsets. And then here you have the y. Here you have a y prime. And I send this one to it. Okay, so when you have a birational map, it's an isomorphism between open subsets. And okay, what is clear here is that if you take you remove the points which are blown up, it's an isomorphism. And then you remove on both sides, you have an open subset. But maybe your point is not there, and maybe you can find still another open subset bigger. For example, if I blow up a point and I blow up the same point, then on the top, any point of the left, it will be the same as a point on the right. So the important thing is that if you have a x identity, that corresponds to x in x. So you have the typical swings where I do nothing. So you have the x contained in B of x. And if you have two different points, they will be not the same because I take the identity, so I compose the identity and I ask that it's the same. So it's really, you put x inside, and then 2 points are the same if they were the same before. So I really, in this bubble space, I have really x as a subset. And then you look at just the space, you don't take the points. Probably, I don't know. You get a cat zero space, but how do you get it? You need to put some distance. I didn't put any maps, any vertex, Ah, yes, yes. Then it's what you did before. Yeah. Mm-hmm. Okay. So you would have some space, but not the same as what you had before. Thanks. Okay, so this bubble space, you have the points of x, and then you have some other points. For example, if I take a point in x, and I blow up, we have x. So I write it like this, blow up of p in x. Then here I have this. Then now what you can check is that any of these points, you have a p1. So because in algebraically closed, they have infinitely many points there. And any point, this is a new one. This is not equivalent to anybody here. Because if I take my definition, it will means that this morphism from here to here should be a local isomorphism, but it's not a local isomorphism at the point. You contract the whole curve onto a point, so it will be not defined. So you have no open subset which is isomorphic to here. So you have x, and then for each of the points that I blew up, I have a point more. Okay, and now you can continue. These are new points. New points. And now I blew up new. Okay, I blew up the point red. So I will not write what is blow up of the blow up. It's not really common to give a name. But now you have really new point file. Again, points and points and then you should think about this. You have a kind of relations between the guys. So I will give a relation. I don't know if it's a cat-zero complex, but I will give a relation. You say that y, usually when you have y pi, the triplet, you just call it with a point, but you have to remember where it was. So we say that infinite linear y if this correspond, so you have so you have two guys like this, and now you ask that this map that I said, not a like isomorphism, but just a morphism. Is defined at y and sends y on 2. Okay. And then okay, with my definition, y is infinitely linear to itself, which is a bit strange, but I don't know if it's a good notion to say. But I mean, we want to say that these points here, they are all infinitely linear to this point. And these points red, they are infinitely linear to this point, but also from this point. And then you can speak about the first neighborhood, which is this is the first neighborhood. I'm not sure. And then the second, these are in the second neighborhood. You have to say how many times you blew up. No, it's kind of a order. It's a partial order. You have a, yes, you have, we write it like this normally. At least it's in algebraic Caminara, you write like this. And then you have, it's a partial order. Because if you are, both are in the both sides, then it will be equal. Okay, then you have this bubble space. And now we can work with this. So when you have a birational map, the set of base points is in fact in the bubble space. So it's a finite subset of the bubble space. So you have a birational map between two varieties, two projective surfaces. Then you have write it down. You have the base points, which are the points in bubble space of X. Okay, maybe for after I will explain that if you have a birational map, birational map between smooth projective surfaces, then you will have a morphism like this, and this will be birational morphisms. And then what you have is that this is a sequence of blow-ups, and then here also. And then what you will have is that the base locus, it's a finite subset. So it's the point where it's not defined. So if you have a point in X, you can say when it's not defined or it's defined, so it corresponds to some subset of this. But if you have in general, in the base locus, you could have a map from something like X prime and then a point here. And you can ask if this map is defined. And then you will have only finitely many elements in the base locus. Here, this will be in the bubble space. So here you will have a is in if phi is not defined at P. Okay, so you have finitely many points. You blow up the points which are not defined, and afterwards you have a morphism, and then you will have a bijection afterwards between you will take all the points and it will be correspond to the so in some sense when you allow all your maps not only base points but not only points on X but also in the bevel space, you have a bijection at the end on the top, and you have just finitely many which are not okay on both sides. Okay, I will not really use this, but just to say that it can be useful for studying birational map, that you have this just finitely many which are not defined, and then the rest just a bijection. And now, what is interesting also is that geometrically, you have points of X which correspond maybe to points infinitely near and conversely. So sometimes you have points which go up, go down, and then sometimes it's useful for when you want to iterate what can happen. Maybe you have points which goes higher and higher, can be helpful. Okay, so now if you take for birational morphism, so you have P pi from Y to X, still all are so smooth birational. Projective spaces, birational morphism. Then the base locus of you can see it as a sequence of blow-ups, and then you can I blow up of I in I minus 1 like before, and now the base points of pi minus 1 is just the union of the I xi minus 1, and then the map which goes to the top. Okay, it's a subset of the x. So you can do this for the maps which are defined, and then you can do this here, and it will be the base locus here if you take it minimal. So if you don't have contracted on both sides, two things which are minus 1. Okay, I will go back to this afterward. The chairman is leaving. When is it finished? A quarter past, okay. I have still 35 minutes. Okay, I wanted to ask him, but he just left. Maybe he knew I would ask him questions. Okay, so now we will use these blow-ups and the intersection form. So, intersection form. On surfaces. So I will need intersection form on surfaces. So position. If you have a x smooth projective surface. Again, if you want to look, you can look on Archer. 5, 1, 1. Then you have a smooth projective surface. There exists a unique bilinear symmetric form. So you take the divisor of x. So for me, it's so it's smooth. So you can take a Cartier vial, but for me, I will look at more on the divisor, and you take just curves, sum of curves, and then you make a group, and then you have the divisor, and then you have a map to Z. And usually people write it as times, like a product. It looks well with it's bilinear, so it really looks well with the product. So it's sum of C times D plus E is C times D plus C times E. And then, so this is a bilinear form. What it should have such that, maybe I write it here. So it has some properties which are important. So 1, if CD are smooth, irreducible curves, for me, maybe I will always assume irreducible in this case, meeting transversally. Then what is this? Just the number of points. So what means transversally? They are smooth, so you have a point, you have C, you have D. So transversally means this. It means that you have the tangent space there of the point. So it's a surface, so it's dimension 2, and you want that the two directions should not be collinear. So locally, it looks like lines in A2, and you want just that the line is not the same. So okay, so not this. This is the thing you should have in mind. So if it's like this, you count for 1. If it's like this, we can put an intersection multiplicity there and make a sum, but I will not do it now. And now if C prime are linearly equivalent, and then C times D equal to C prime times D for all D. Okay, so if you have this, then in particular, it gives you an intersection form on the pK. Because it's defined up to equivalence, so you take the class and you write it like this. Okay, so not so easy to prove it. I tried many times to prove it in my lecture, but it was too long. 1 year of lecture algebraic geometry. I had problems too. When you want to define everything, it's long. So there is a proof in Hartshorne, but he used a lot of commutative algebra before, so I'm not so sure it's so easy. Okay, but it makes sense and it's not natural. So for an example, if you take x P2, then you get Bézout theorem. So this is one other proof that I know that I can explain you after is that I do first Bézout theorem and then I can prove this on all the blobs of P2 and all contraction of P2. So for rational surfaces, it's not so complicated, I would say. Okay, so then it's correspond because you have C in P2 and D. These are curves of degree M and N respectively. Then C is equivalent to M times the line, and D is equivalent to N times the line. So if you have C times D, because it's up to equivalence is the same as M times L times N times L, and that's good because you write it as a product like you could multiply, and it's exactly the case. So you just have M times L minus L square. L square is a line, but two lines are equivalent and they meet in one point transversally, so it's 1. So, corollary, Bézout theorem, if you have a curve of degree M and a curve of degree N, if they intersect transversally, they are exactly M times N points. Okay, afterwards, you can be more precise when you know that it's unique for this. You can show that if they intersect not transversally, but for example, like this, then you have to count something. So here it looks like 2, but not so clear. If it could be 4 also. And then you can count for each point and you get something positive. So what is important is that if you have two curves without common component, the product is positive, non-negative. Just a sum of intersections. Okay, I will explain this. Then we blow up points and find that the intersection, when you do one curve times itself, it's called self-intersection. And for a point, it will be -1 curve because it will be self-intersection -1 for the blow up. So we will use all these things to prove the Noether-Castelnuovo. So intersection, when you blow up, that it decreases, and intersection with exceptional curves. Not here. Okay. So now we can speak about the multiplicity of a point, of a curve at a point. So what is the multiplicity of a curve at a point? Okay, what is this? If you have a P inside X, so curve, smooth projective surface, it's not very important here. Projective, because it's some question which is local. And then you take a point. Or maybe not necessarily in C. Okay? Now you define the multiplicity of C at P. Okay, so one version, you could say you take a local equation. So because it's smooth, at a local, in a neighborhood of P, this C is given by one equation. So it's a rational function which is defined at P. Maybe it has some poles, but you remove them and you're on an open subset which contains P, and then it's a regular function. And then just a irreducible element there, and it defines the generator of the ideal of the curve. Okay, so you take the local equation, and now you ask if, because if it's in the maximal ideal to the power k, but not to the power k plus 1 ideal of OP X. So that's the definition of the multiplicity. Okay, because it's a curve, it's not zero, so there is the end. And with this definition, you see it doesn't depend on the curve coordinates, but if you have a variety which is let's take case where you have P inside U inside X, where U is isomorphic to A2. In fact, this will be the case in all my examples. So it's an open subset. Then the curve inside U is just given by the zero set of one equation, and now it's a polynomial. And then now you just write it Fi homogeneous is homogeneous of degree I. Okay, so yes, completely. Yes, that's important, otherwise it's stupid to do this. Okay, and then what I ask is that, in fact, we can check the maximal ID in this case. Here, M is just xy. So it's just in the local ring will be just polynomials divided by polynomials, so that downstairs is not 0. And then it just generated by this. And then the question is just M, the multiplicity. Yes, this is K. This is the point. I didn't want to write it on the top because it's too much. Okay, then is the smallest I such that Fi is not 0. Okay, so you write it as it has a degree something, let's say D, we didn't know it's finished or not, it's not important. It's bounded there, but then it's also, of course, bounded there, and then you take the first one, which not vanish. So what you can see in this differential or on the other one is that MP of C, so it's 0 if P is not. In C, it will be, say that the constant term is not 0. Is 1 if P is a smooth point of C, and at least 2 if P is a singular point. Okay, so it's kind of measure of the singularity at the point, because there are many other measures, not the best, not the only information about singularity, but it's enough for us for the moment. And then we'll use this with blow-ups. Yes, that I will prove. Uniformation. That's a very good question. Yeah, maybe I can advertise this question. Important. Smooth projective variety, rational, and P is a point. Does there exist U open with P in U, so a neighborhood, such that U is isomorphic to AN? That's my question. And weaker is a strong question. I don't know if the question can be strong or not. Okay, and the weak version maybe. U is isomorphic to V, which is open. That's maybe the second, which is more famous. And for dimension 2, I will prove that both are true. Dimension 3, I don't know. Dimension higher, I don't know. So neither of them. Okay, so it would be funny. Maybe I don't even know if the strong version is false. Maybe it could be true. But yeah, I don't know. Okay, so if it's rational, yeah, that's the question. Still a question. Yeah. There are some attempts to do this, but just attempts. Yeah. I mean, there are cases where it's proven to be true, but in general, it's not known. I mean, if you have a variety which satisfies this, for example, Pn, of course. Exactly. So it's called uniform rationality. I will maybe write it now. Then Pn is like this. And in general, if you have a uniform rationality variety, then if you blow up anything, it's still like this. But then if you contract, we don't know. So in dimension 2, yes, I know everything. I will tell you and I will prove you that it's the strong version. And it's even stronger. You can really count how many, you can cover any surface projective by some finite number of A2, and you can calculate how many A2s you get. There are some results on this. Okay, so I will tell you this probably in days, I would say. Okay, but in dimension 3, good question. In fact, it's a question on Matherbor flow, which had, I don't know, like 100 points for the question, and no answer for the moment. Okay, then why it's important, this multiplicity. When you have a blow-up, I will explain what happens for this. So if you have a pi x to y, maybe I will write it like this. Blow-up of p. No, maybe I will do y in x position. So again, you can find if you want to. 5, 3, 2. Okay, then you take a blow up of a point, and then you have E is the pi minus 1 of the point. So as we saw before, it's a P1. So XY smooth projective surface. In my lecture, there will be only this, but they call it. Then it's isomorphic to P1, and then what you get is that it's a curve, closed curve, so it's an element of the pk in Y, and then you can compare the pk. So what you get is that pk of Y, it is equal to this. So you can take the pullback of a divisor. So now what you want to do, yeah, there is something missing otherwise. You can take a divisor, you can put it back. So now it's better, it's smooth, so you can choose Cartier or Weil divisor. It's better to take Cartier. Now you have an equation locally and you just take it back. And now it's easy. Now you know what it is. And you can, what's important, you don't lose any information, so it's really isomorphic to this, and then you just add one guy more. So as a Z module, it just rank one more. Or if before it was very large, would not make more sense, but interesting. And the intersection, you know, if you know what happens here, you know everything on Y. So what you get is that if you intersect something which comes from X, well, it's the same as what you did with X. What you add is orthogonal to anything what you had before. And important thing also, E times E, that we call write usually E square, is minus 1. Okay, so the first time we see this, it's a bit strange to have an intersection of two curves which make minus 1, because when you intersect, you should have finitely many points and some, but here it's the same curve twice. So you cannot... in fact, if you want to calculate this, you have to write E as a difference. So you take a curve passing through the point, you take it back, and then you write it as a difference of two things, and then you intersect E, and you will check that you get really minus 1. Okay, so that's what happens when you blow up a point. So on the pk, you have an intersection on both sides. And you know everything. Ah, I should use this. No, okay. Will not destroy to do this. Okay. Now we can use the intersection, the multiplicity, to get what happens for curves. So we'll take a curve in the surface. I will blow up a point, and I will look at what do I get on as a strict transform in the pk. Okay, so lemma. So X smooth projective surface. Blow up. I blow up a point. And now I take a curve. Irreducible curve, so closed. Then what you get is that if I take the pullback of the curve, so I take the equation locally and I take it back, then it just the strict transform of the curve plus m times. So this is an equation in peak. Y. Okay, so I take the equation, I take it back, I create something, then I get the strict transform, and then some multiple of the exceptional divisor, and this is the multiplicity. So in general, you could define a multiplicity like this also. You can just take, I blow up, I take it like this, and that would be the multiplicity. Okay, then I will do a proof. In the case where it's if x is uniformly rational. Okay, in my lecture, it will be always the case. So you have a C. So locally in A2, C is given by a polynomial pk y, maybe not k, maybe m plus pm plus 1 plus pd equal to 0. M is the multiplicity. So this is not the same, not 0, and they are all homogeneous of degree. So pi homogeneous of degree I. Okay, so write a curve like this, and then I look in a affine chart. So the blow up of A2 is, we saw before you have two charts, so I can choose one of the two. I just want to see what happens. So in fact, what is clear, I mean, I didn't say, but what is clear is that this is a formula with a number on there. Because outside of the point and of the exceptional divisor, it's an isomorphism. So it has to be this plus a multiple of E. I just want to know this number. So I can choose any of the two charts because E is on both. So you have the blow up is given by A2 to A2 U V U V. Okay, and you just replace. And then you get the pi star of C is given by just, I take the equation, it's a Carty divisor, locally just this, it's just this polynomial, and then you take it back, so you replace. Okay, but now it's homogeneous, so I can take a VM here. This is Vm plus 1 and Vd. Okay, so what I get is that at the end I get Vm times something, which is V plus Vm plus 1 to 1. D minus M P D U1. Okay, so what I did, I just took the equation, I take it back, and then I get a new equation. So this is vanishing on the exceptional divisor. The exceptional divisor is exactly V equal to 0 because it's what is contract on 0, 0. So this is exactly M times E, and this is just E times. So that's the end. This cannot be something else. There is no V there, and outside I know it's an isomorphism. Okay, then we have just this formula now, and we can use this to play with blow-ups. Okay, now the last position, the S smooth projective surface. CD distinct irreducible curve. Then what you have is that before I knew that if C times D, if it's their transversal, it's just the number of points. But now, what is interesting is that it's even if it's not transversal, I can know what it is. It's a sum so of the multiplicity okay, so I just have to define what it is. I will prove that. So what is this? If you have C inside S, and then this for any element in the bubble space, I have P, let's say Y, and then pi. So I have Barrage morphism, and now I have here C. Then what you get, you take the strict transform. Maybe I should. You have your point there. You have strict transform, and then just this is just the multiplicity. You have the multiplicity at the point. So I take the strict transform, and I calculate the multiplicity. So for each point in the bubble space, I have this, which is an integer, which is sometimes 1, sometimes 0. Most of the points is 0, but sometimes it could be 2, 3, I don't know. And then I have this. And then in particular, there are only finitely many P in the bubble space with MP bigger than 0, and in fact, if you take a curve, you have infinitely many points which are multiplicity positive, because you have all the points on the curve, but also when you blow up, each time you get a new point, you have infinitely many, but you cannot have positive multiplicity for both. I think I have 4 minutes. Maybe I will prove this tomorrow. So not to be in a hurry and go sketchy for the proof. It's a bit technical, so and it's interesting. So I will do this tomorrow. But if you have questions.
Questions for Jérémy?
Rugby player.
Hi. So for the bubble space,
Yes.
Is this an alternate description of it? Can you take the inverse limit over surfaces which have a birational morphism to x, and where the inverse system is given by like x prime dominates x double prime?
Yeah, it's exactly this. It's
Okay.
exactly this. Yeah.
This is what I was thinking. I've never seen your.
Yeah, it's really you have it corresponds to this here. You can have more and more points here.
Yeah, and you probably have to use some like universal property of blow up to justify my construction.
Yes. I think it was first introduced by Manin with this technique. It's 30 years ago, 40 years ago, even more. It was 30 years ago when I started.